It should make sense to us. It should make sense to us because the probability of 3 parts being defective is quite low, right? I mean, the probability that even 1 part is defective is very low. It's 1 in 1,000. So the fact that you could pick 25 parts and get 3 of them being defective is extremely small, right? So it shouldn't surprise us that this number that we found is in fact, very, very, very small, because it'd be quite unlikely to find 3 defective parts at once. More likely would probably be that none of them are defective, right? That in fact they're all good parts. So again, we go 25, choose 0. Because remember, we have defined P, the success, as being a defective part, times 0.001 to the power of 0 times 0.999 to the power of 25, right? 25 failures, 0 successes, and there's only one way to do that, of course. This one is 25, choose 0. So let's go back to GeoGebra here and work out what it is this should be. So let's change so the calculation is still the same, right? P that x equals s is equal to, and choose s times p, just quickly write this out so we don't have to keep writing it over and over again, p to the power of s times q to the power of, and we need n one more time, n minus s. Okay, and again, let's just get these to be, that's fine. Okay, so this is the formula we're always using, right? The probability that x is equal to whatever value is 25, choose that value, and so on. Let's change our number of successes to 0. Now our probability that we have 0 defective parts is 25, choose 0, 0.001 to the 0, 0.999 to the 25, okay? Now, when we actually calculate this, the actual result of this, right? Let's just grab it from before. Put it in as a number. Okay. Our probability here of this occurring, and maybe round this to a more reasonable number now. So there's a 97.5% chance that none of the parts are defective, which is quite likely. I mean, it was only 1 out of 1,000 that they would be likely. So in a batch of 25, 97.5% of the time, we would not expect to find any defective parts. Again, all we had to do this was plug in the number 0 into our equation for 0 defective parts and work out the probability. Okay, so we'll write down our answer, 0.9753. 0.9753. Now, at least 1, remember, at least 1 is the complement of none, right? What is the opposite of none? Some. What does some mean? At least 1, right? So the opposite of none is at least 1. So this question is very simple. We just look at the one above it, right? And we go, let's do the calculation here. Oops. So we'll go 1 minus a, and we arrive at the answer 0.0247. Okay, that's easy. It's just the complement of the one above. So we go 1 minus 0.9753. Let's just put this down on another line. Okay, we have 1, which is all the possibilities. Subtract all the ones where you had none, and that was this, right? And again, in terms of a formula, we're doing all minus the complement equals the desired outcome. Now, 2 or less are defective. Okay, there's no quick way to do one like this, unfortunately. We need to go the probability that x equals 2 plus the probability that x equals 1 plus the probability that x equals 0. these are the three different options, the three different ways that 2 or less parts could be defective. Now, we already know that px equals 0 is 0.9753. We've done that already. What we need to know is the probability of 2 being defective and 1 being defective. And I'm going to go out on a limb here and guess that if the probability that 3 was defective was, whatever, 6 zeros and then a 2 5, right? It was very, very small. I doubt the probability of 2 is going to be very high, and even the probability of 1 is not likely to be very high. I mean, we've only got 2% of the sample set left to work with. In any case, let's work this out quickly. If we use all our exact same equation but change s to equal 1, we have x equals 1. Okay, 25 choose 1, 0.001 to the 1, 0.999 to the 24. Okay, that should make sense to us. We're just using the formula, same formula as before. And we arrive at a 2.44% chance. Okay, 0.244 chance is that one item is defective. Now again, let's calculate the probability that 2 items are defective, although really this is going to be exceedingly small. Let's change s now to 2. And we go x equals 2, okay, 25 choose 2, 0.001 to the power of 2, 0.999 to the power of 23. And we get as our answer 0.003. Again, a very, very small probability, which should make sense to us. Okay, and this would be then our probability that, that 2 or less are defective. Remember, or means we're adding stuff up. So let's quickly add these up here. 0.003 plus 0.9753 plus 0.0244. And again, the number is so close to 1 that we need a lot of decimals to be able to see that it's not, right? In fact, it actually is 1 the way I did it, because I did it by adding up the rounded numbers, and the rounded numbers, of course, makes sense, would actually make 1. So we'd have to round up we have to add up, the unrounded numbers to see the original answer, right? Which is quite high. You're going to get a 9999994 or something like that, right? Essentially, so px is less than or equal to, p that x is less than or equal to 2, okay, is approximately 100%, right? It's let's just write approximately 1, right? It's we know it's accurate to 6 decimals or thereabouts. Right, whatever it was we worked out before in this above question, it's approximately 1. Okay, and that should make sense because it's extremely unlikely you're going to get that many defective parts here. Okay, the beautiful thing about the binomial distribution, and the thing that you should probably be worried about if you're thinking about what we have done in the past, the last 2 days, right, was calculating the expected value. And remember, the expected value is equal to x times p of x, right? Adding up all of them, sum of all x p of x. And this should have us a bit worried about the binomial, because all of a sudden the binomial, I'm throwing at you 25 different possibilities. 1 thing could be defective, 2 could be defective, 3 could be defective, 4, 5, 6, all the way up to 25. To do this the table way, where we do each x times its p of x, is going to take us forever. Luckily for us, there's a brilliant and beautiful formula that solves this for us instantly. The expected value of any binomial distribution is simply NP. And this saves us so much time because we have no need to go through the table method when we're looking at a binomial expansion, a binomial probability distribution. The expected value of any binomial distribution is simply equal to n times p, right? So it's very, very quick, does not take a lot of work, just remembering that relationship, okay? Very important relationship, underline it, highlight it, whatever you need to do. Okay, refer back to example 2. What is the expected number of defective products if the customer purchased just 25? Well, the beautiful thing about this is the expected value is just n times p. That's very easy to do. We know there were 25 items, 0.001, so we end up with, I said 001. E of x is equal to 0.025. So we expect to find 0.025 defective parts in a sample of 25. Okay. Once again, notice that the expected value does not make sense on a literal level. We are never going to find 0.025 defective parts. Remember that the expected value is a long-term average, not a prediction for an individual case. Right? Remember that difference. Very, very important. Okay. Last, I guess we have 2 more. So second to last question for today is this one. 25% Smarties manufactured are red. On the production line, Smarties are randomly packaged 20 to a box. Okay, what is the probability that 4 candies in a given box are red? What is the probability that at least 4 candies in a given box are red? Right? Many kids are disappointed to find only 6 red Smarties because they're her favorite. Sorry, that doesn't say many kids. It just says Mary. It's her favorite. Should she be disappointed to only find 6? Okay, so let's take a quick look through this question. Probability that 4 candies are red. Okay, so reminder to get started with this one. N is how many Smarties are in a box. It's 20. P is the probability that you get a red Smartie, which is 0.25. Q is the probability of failure, or an inferior non-red Smartie, which is 0.75. Lastly, we are looking at the number of successes we are interested in, which is x, and which we are going to say is 4. We're looking for 4 successes, right? So let's just use our handy calculator back here to do this. So let's make some quick changes here. I'm going to blow this up a bit bigger. You have a better time seeing it. And we certainly don't need that many decimals anymore. Okay, so again, let's make some quick changes here. N is 20 now. Successes we're looking for is 4. Okay. Probability of success, which is P, 0.25. Probability of failure is 0.75. And that's about it. So we look here. This is what we're doing, right? Probability x is equal to 4. 20 choose 4. Success to the power of 4. Failure to the power of 16. And we arrive at this answer. So we can cut this down, I think, one more. 1897. 0.1897. Okay, so 0.1897. And in terms of a formula, oops, typical. Right, where did this come from? It came from here. Right, we plugged in n is 20, p is 25, 0.25, q is 0.75, x is 4, and we just subbed everything in and calculated. Okay. What is the probability that at least 4 candies in a given box are red? Okay, let's go 0, 1, 2, 3, 4. I'm going to do the complement here, right, obviously, because I don't want to calculate. I want to add up 5, 6, 7, 8, 9, 10, 11, 12, all the way up to 20. I'm going to do the complement. So let's do the complement. So 1 minus the complement. So what is the complement, right? X could be 0, 1, 2, 3, or 4. We've already solved 4, 1897. We need to solve 0, 1, 2, or 3. So again, I'm going to do these fast. We don't, hopefully you've got the idea by now how this works. I'm just going to, plug into the formula that we've been working with and just calculate these quickly, and then at the start of the next video, I'll have them done.